Hello everybody, this has been one of the more anticipated videos that I've wanted to make, and I'm very excited to do it. Today we're going to be going over every single important feat that you could ever want inside of One Piece. Now, I must warn you, as you can probably see yourself, this video is going to be much longer than my normal videos. Because of its sheer length and everything that goes into this video, I am breaking it up into multiple sections and they will be labeled for you so that you can get to each one as you would like. In further videos where I talk about scaling of different people and I talk about other verses, I'm going to be doing this to make it easier for everybody to get to the certain calcs that they need to see. Now, I am making it easier on you guys to find these calcs, but I still would really love it if you could watch the video all the way through and kind of go with me as I'm talking about these feats, because we're starting at the very beginning of the series and we're kind of getting to re-experience all of these feats and getting to know them a little bit better with each other. Of course, I will be giving context of the feat before I actually show you the calc, but I'm not going to be going as in-depth because there's no inverse that needs to be done here, as I'm just scaling the verse. I'm not scaling anyone specifically to a certain feat. With all of that being said, let's hop right into the calcs. Luffy saves Zoro from musket fire while he was restrained. Chapter number 5. Zoro is about to be executed in the courtyard when Luffy jumps down from the very top of a building and intercepts a fire from the muskets. For starters, we need to find the size of the cross that Zoro is stuck to. Zoro has a listed height in pre-timeskip at 1.78 meters. In this scan right here, that is represented by 269 pixels. Dividing Zoro's height by the pixel value, we get a value of 0.006 meters per pixel. That compared to the 336 pixels of the cross, that means that the cross is equal to 2.223 meters. Why this is important is because we need to anxize the distance between Luffy when we actually see him in the panel right after it was stated that they were firing, so that we can see how far away Luffy was, because we can't just assume that he was at the very top of that building as he had already started moving. With a panel height of 829 pixels and the cross diameter of 115 pixels, this is equal to 0.19 radians or 11 degrees, which then plugging into the anxize calculator means that Luffy is 11.445 meters away from Zoro. Speed is defined by distance divided by time, which means that we have our distance traveled and now we just need our time frame. We see in an SBS as well as just by the Marines holding them out that these are obviously muskets. Now, these muskets tend to pack a little bit more of a punch than what we have in the real world, but we don't really have a way to quantify that. Off of this study right here, I find out that the muzzle velocity of a musket would be around 434 meters per second. We have our speed that it's traveling at, we just need to find the distance that Zoro is away from them. Since we already found the cross's diameter before, we can go back to the very first panel that we used to size Luffy's distance and just take that cross, which is defined as 115 pixels again. We take the 2.223 meters that we know it is, and we divide it by 115, which gives us our meters per pixel of 0.019. The distance is 211 pixels, which just means that we're multiplying the 0.019 by 211 to find out that they're 4 meters away. Taking our muzzle velocity as our speed, we get a time frame of 0.009 seconds. Taking the distance that Luffy moved, or 11.4 meters, dividing up our time frame, we get a value of 1,217 meters per second, which is Mach 3.5, or supersonic plus Gum Gum Rocket. A very impressive feat for Chapter 5, might I add. On to the next calc. When fighting off against Zoro, Hypnotized Butchie makes a big crater and knocks down part of a cliff. Chapter number 35. This one was a little bit harder to navigate. We're going to have to use a little bit of an unorthodox method to get the sizing of some of the things here. Butchie has a listed height of 216 centimeters, or 2.16 meters. To find the size of the cape, we just take his height of 216 centimeters and divide it by our pixel value of 135, which gives us 1.6 centimeters per pixel. Taking that and multiplying it by our value of 77 pixels, this means that Butchie's cape is 123.2 centimeters in diameter. Because Butchie was bent over, we actually do need to use his cape size. In this scan right here, Butchie's cape size is defined as 21 pixels, so we're taking 123.2, dividing it by 21, and getting a value of 5.866 repeating centimeters per pixel. Multiplying that value by 355 pixels, this means that the crater has a diameter of 2,082 centimeters. Given the nature of cratering, we can't just say that this is a perfect sphere, so we need to find its depth as well. For this, I will just be using the value of Zoro's arm. Once again, Zoro has a listed height of 1.78 meters pre-timeskip, or 178 centimeters. Dividing that by his full body of 301 pixels, this gives us a value of 0.59 centimeters per pixel. His arm is represented by 71 pixels, so multiplying that value by 71, we get his arm's length of 41.98 centimeters. Taking his arm length of 41.98 centimeters, which is represented by 95 pixels, we get our division value of 0.44 centimeters per pixel on this cratering scan. Using the crater depth as the rock that is shown right here, we can find out that the crater is around 68.94 centimeters in depth. Applying this to the volume of a cylinder, we get this large number right here as our volume. As we can see right here, the rocks are kind of flying up in the air in an explosive manner. This means that it can apply for something called explosive fragmentation. A paper that I found right here shows the difference between fragmentation itself and explosive fragmentation, as the kinetic energy is taken into account in explosive fragmentation. This will give us our value of 17.5 joules per cubic centimeter. After multiplying our volume by our joules per cubic centimeter value, we get a total energy release of 8,220,730,000 joules. But we are not done, as he did collapse the cliff that is next to him. In this scan where this is actually shown, we do not have anybody with any listed heights that are shown, as the only person that we could use is possibly Luffy, but he's too far out of frame. This means we would have to use the height of the average person. Based off this study right here, the average man is 1.754 meters tall, or 175.4 centimeters. The man is 175.4 centimeters divided by the 42 pixels. This gives us a value of 4.17 centimeters per pixel. Broken part of the cliff is 592 pixels, which means that it's 2,472.3 centimeters, and its height is 291 pixels, which means that its height is 1,215 centimeters. A low ball for this, instead of going layer by layer, would just be the volume of a cone, which means that it's this large number right here for our volume. We cannot apply explosive fragmentation for this because it was not exploded in the traditional sense, but rather it just fell down after being broken into way larger pieces than before. So we can just use our value of fragmentation, which is 8 joules per cubic centimeter. This gives us an energy release of 15,557,360,000 joules. Adding the two together, since they were both completed at the same time, this would give us 2.3 times 10 to the 10th joules, or high-rise level Hypnotized Butchie. That's quite a lot of energy for Syrup Village, don't you think? Anyways, on to the next calc. While fighting Arlong, Luffy uses Gum Gum Battle Axe to bring down Arlong Park, fragmenting it into very large pieces. Chapter number 93. To start off, we need to size the section of the outside building. In this scan right here, Arlong is standing next to a few of the average fishmen. As we can see in the back, one of the fishmen is also leaning up against a pole. As we do know, Arlong is a large fishman, so I'm going to be sizing one of the other fishmen because they are taller than normal humans, so we could get that as the average size for a fishman. Arlong has a listed height of 2.63 meters. 2.63 divided by his pixel value of 193 gives us our 0.013 meter per pixel value. The other fishman is 169 pixels, which means that he is 2.3 meters tall. In a shot more zoomed out, we can see that the fishman is still standing next to this pole, and we can get the size of the outside of the building and those little roofs above him. As shown before, he is 2.3 meters tall, divided by his pixel value of 140, gives us our meters per pixel of 0.016. The roof is 353 pixels, which means that it's 5.8 meters in diameter. Because this is an oddly shaped building, I could go through layers by layer and getting the volume per section, but I think it's just safer to use a cone for this. In this scan right here, we can see the entirety of the building that Luffy did destroy. Taking our roof diameter and dividing it down by its pixel value of 159, this gives us 0.036 meters per pixel. Arlong Park's total diameter is 824 pixels, which means that it's 30 meters or 3,009 centimeters. The height of Arlong Park is 891 pixels, which means that it's 32 meters or 3,253 centimeters. Once again, using the volume of a cone and taking into account that this is a hollow building, which means that we're removing 80% for its hollowness, we get a volume of 1.5 times 10 to the 9th cubic centimeters. As I've stated before, the fragmentation of granite would be at 8 joules per cubic centimeter, which means that this is a total energy release of 1.23 times 10 to the 10th joules, which means that this is high-rise level Gum Gum Battle Axe Luffy at Arlong Park. Boy, do I love the consistency of power cliffing. Next calc. Zoro is seen moving vast distances to catch the bounty hunters of Whisky Peak off guard. Chapter number 107. Zoro is standing atop a building when he learns that the people of Whisky Peak are not as genuine as they seem. Because they are by one of the entrances of the Grand Line, the people of Whisky Peak pick up the bounties of the stray pirates that come into the Grand Line. Because we do not have the listed height of a lot of the people that are here, we can just use the height of the average person to size the relative area that we see Zoro ending up. Changing the value a little bit because of the new study, the average height of the Japanese male that we'll be using is 171.8 centimeters or 1.718 meters. The panel has a height of 1,293 pixels and the person has a height of 33 pixels. When plugging into the ing size formula, we get to see that the distance between Zoro and the bounty hunter is 47.067 meters. In that panel where we see Zoro actually move when everyone is caught off guard, we see that Zoro moves behind the mayor but is still in front of the man in the hat. So I just ink size to the man in the hat because going to the guy that is closer just wouldn't really make any sense. In this study right here by MIT, which will be linked in the description below, we found out that people can react to things in as fast as 13 milliseconds or 0.013 seconds. The average person in this study, after short amounts of exposure, can react to stimulus up to 13 milliseconds. And that is the point of this study, and that is the lowest value that we get, which can be applied to most of these circumstances, which means that here on out, the value for perception blitzes will be 0.013 for our time frame. Taking the distance that Zoro moved, or 47 meters, and dividing it by our time frame, which is the perception of 0.013, we get 3,620 meters per second, or Mach 10, which is hypersonic plus Whisky Peak Zoro. I guess that's why you don't mess with the Straw Hats. Next calc. A statement is given of Ace stepping onto Drum Island, causing the island to stop snowing for an entire day. Chapter number 154. First thing that needs to be noticed when we're talking about Drum Island is how it's comprised of multiple very large mountains. Mountains that are in further perspective are absolutely dwarfing cities that are closer to us. This lets us know that these are very large mountains, as well as the fact that we can see Luffy on top of it, but that doesn't really represent how big they are, because I think the whole point of that panel was Oda trying to tell us where Luffy was and what he was going to do, as he was using Gum Gum Pistol. Newer information comes out about mountain classification all the time, and they're split up between 7 main classes. These classifications range from Class 7 all the way up to Class 1 being the biggest. A Class 7 mountain would have isolated basins and plateaus that wouldn't exceed 25 square kilometers in area. A Class 6 mountain would be elevated between 300 and 1,000 meters. 5 mountain would be elevated between 1,000 and 1,500 meters with a slope greater than 5 degrees. Class 4 mountain would be elevated between 1,500 and 2,500 meters with a slope greater than 2 degrees. A Class 3 mountain would be elevated between 2,500 and 3,500 meters. A Class 2 mountain would be elevated between 3,500 and 4,500 meters. A Class 1 mountain would have to exceed 4,500 meters in elevation. Given these classifications, as well as how they're dwarfing the cities below them, I think that it's safe to say that this mountain would be at least 2,000 meters in its height. In a zoomed out panel before the Straw Hats actually reach Drum Island, we can see the entirety of the island compared to its biggest mountain of 2,000 meters. Taking the largest mountain, which we just determined was 2,000 meters, and dividing it by its pixel value of 32 pixels, we get that our division value is 62.5 meters per pixel. Taking that and multiplying it by the diameter of Drum Island and its pixels, we get that the entirety of Drum Island is 12 kilometers or 12,000 meters in diameter. The image where they're talking about it and where they're recalling it, we see that there's no clouds above Drum Island, which means that Ace probably got rid of the clouds in the area. When we take a look at vertical cloud structure, we find out that the average cloud would be around 1.5 kilometers thick. Treating the clouds as a cylinder, as we can't really justify Ace cleared any more of that, that would mean that the clouds have a volume of 1.6 times 10 to the 11th cubic meters. Multiplying that by the density of clouds, which is 1.003 kilograms per cubic meter, we get a mass of 1.7 times 10 to the 11th kilograms. Because this is heating up, we're going to need to find the latent heat of condensation of the clouds that are in the given area. This formula right here will determine the estimated value of the height in the clouds and how much they would move. Taking the altitude of the cloud, adding it to the height of the center of the cloud, multiplying that by 2, then dividing it, we get our estimated value. You can't just use the standard cloud height of 2 kilometers or 2,000 meters because we know that these mountains are much taller. So we're going to be using the mid-sectional area of 4 kilometers, which will give us our value. Taking our 4,000, adding 7,000, multiplying it by 2, then dividing, we get 11,000 meters. This graph right here shows that clouds would decline 6 degrees per every 10,000 meters traveled. Taking our 6 degrees, multiplying it by the distance that we have of 11,000 meters, and then dividing that by 10,000, we get 6.6 degrees were lowered. To solve for latent heat of condensation, we first need to get the cloud temperature. To find the cloud temperature, we're just taking room temperature and we're subtracting it by our previous value of 6.6, which gives us a 15.4 degrees Celsius temperature change. Plugging into the formula for latent heat of condensation that's shown on the screen, we find out that the joules per gram is 2,464. But we are not done yet. To find the energy released from the cloud vaporization, we use the following formula, which is defined as energy equals the latent heat of condensation of the cloud in joules per gram multiplied by the mass of the clouds found. Plugging in what we just found, hypothetically, Ace could be releasing 4.1 times 10 to the 17th joules, or city levels of energy, by stepping foot on Drum Island. With all of that being said, let's move on to the next calc. While standing off against the Sumigiri guards of Alabasta, Crocodile moved so fast that they didn't even notice they got hit. Chapter number 196. See that the Sumigiri guards attack Crocodile, and then he moves in his sand form straight through them, and they look up at him as he's at the top of the building afterwards. They don't even notice they got hit as they're talking, and they say that he's not even gonna fight. But he did fight, as he already attacked them and they didn't even notice. For starters, we need to know how far he moved, and we can say that the minimum distance that he moved was from the ground where he was standing up to the top where we can see him afterwards. Using Nico Robin's height of 1.88 meters, we can figure out how tall this is. Nico Robin, who is 1.88 meters, divided by the 56 pixels she represents, gives us a 0.03 meters per pixel. The distance to the top of the building where Crocodile is sitting is 613 pixels, which means that it's 20 meters in the air. For this, we're going to be talking about something that is known as a tactile blitz. A tactile blitz is a term coined by Manifest in favor of the person who actually found this type of reaction. There are receptors that lay between the skin cells and the upper epidermis of your skin that can respond to a given stimulus at a frequency of 350 Hz. Hertz is a unit frequency system that would define the cycles of movement in a single system. 350 Hz would mean 350 cycles in a single second. 3 Hz is 0.33 seconds, and so on and so forth. That means that 350 Hz would be 2.857 milliseconds, or 0.0028 seconds. Which means that if you were to get touched and there was a delayed reaction, as in you didn't understand or you didn't know that something happened to you, this would qualify as a tactile blitz. In these cases, you only use the distance a person traveled after the given stimulus is set, which means after he was hit. So because he went out before he got hit, we wouldn't take in the distance that he actually moved out towards them, but only the distance from them to up in the air. Since we just determined that the distance to the top of the building is just over 20 meters, we can take the 20 meters and divide it by our time frame, and that gives us 7,202 meters per second, or Mach 20, which means that Crocodile at Alabasta is hypersonic plus. I love it when smart people find specialty values for us to use. It's very nice. Next calc. When the war wages at the heart of Alabasta, Crocodile creates a sandstorm that appears around the outer edge of the capital. chapter number 198. To start this off, we need to find out how big the golden globes are at the top of the Capitol building. For starters, we need to find out how big this opening is of the doorway. For that, we can use the pillar size, as there's someone that stands next to it pretty much at all times. One of the guards named Chaka is stuck to the pillar that leads up to the top. Chaka is 2.13 meters tall, dividing it by his pixel value of 234. That gives us 0.009 meters per pixel. The pillar is 123 pixels, which means that it's 1.19 meters in diameter. In this next panel, we can see the reference of the pillar to the entire opening of the door. Taking the 1.19 meters and dividing it by its pixel value of 24, we get 0.04 meters per pixel. Then multiplying that by the opening, which is 423 pixels, we find out that the opening is 19.7 meters. We can finally move on to the ball size, as the opening here, which is 19 meters, is represented by 106 pixels, which means that we get a value of 0.18 meters per pixel. Multiplying it by the ball's pixel value of 301, we get that the ball is 56.03 meters in diameter. In a zoomed out shot, we can see the entire tornado of sand that he creates next to the ball. The ball, which is 56 meters, dividing it by its pixel value here of 51, we get 1.098 meters per pixel. The storm's diameter is 1,459 pixels, or 1,600 meters. Given the height of the storm being 423 pixels, that means that it's 464 meters in total height. Once again, using the volume of a cone, we find out that the volume of this is 3.12 times 10 to the 8th meters cubed. When looking up the density for sand, we get a bunch of different values. As quoted by this Dream Civil study, we find out that this density of sand has no consistency to it. Different densities based off of a bunch of different things, like if it's loose, if it's packed, if it's wet, and if it's dry. For this, we could just use a baseline value of dry sand and say that it's 1,600 kilograms per cubic meter. This is when sand's in its most undisturbed and natural form. Sand is in its most natural form when it's been partially compacted by rain and gravity, but is now dry. To solve for mass, all we need to do is take the volume and multiply it by the density, which we just found. After we multiply those two figures together and take out some of the volume considering that they're fighting on the inside, which means that it's hollow, we get the total mass to be 175,094,640,000 kilograms. For this, we're going to be solving for rotational kinetic energy. We could assume that 90 degrees of rotation would happen over the span of 10 seconds due to the fact that everyone couldn't even react to it starting. To find for our radians per second, we're taking pi times the radians divided by 2, and then dividing that by 10 seconds, and we get 0.15 radians a second. Radians per second is a unit of angular frequency, which is what we would find when we're solving for angular velocity. To find the energy of a moving mass, we're taking 0.5, we're multiplying it by its mass, and then we're multiplying that by the radians that we just found squared. Once plugging that in, we get 4.16 times 10 to the 14th joules, or large town level crocodile at the end of Alabasta. I don't know about you guys, but I'm definitely loving this consistency. On to the next calc. Upon one of Enel's first appearances, he launches an attack called Thor, which vaporizes a big portion of a giant tree, as well as the ground beneath it. Chapter number 241. Feat is completed when the Straw Hats are separated and Nami is coming up on the shore of Skypiea. For this, we could very easily just figure out the size of the areas based off of Nami. Nami has a listed height of 1.69 meters. Taking that 1.69 meters and divided by her pixel value of 11, we get 0.15 meters per pixel. Tree height, which is 1,189 pixels, would give us a height of 182 meters. The diameter of the tree, as well as the diameter of the crater, is 548 pixels, which is 84 meters in diameter. Because we're taking the volume of the tree first here, we're going to find the volume of a cylinder. Once applying that, we can find out that this volume is 9.2 times 10 to the 13th cubic centimeters. Now, finding values for destroying trees is absolutely insanely hard to find. I do have some values for pulverization, and I have some values for fragmentation and violent fragmentation, but when it comes down to vaporization, there's just not a lot for it. When looking on Google Books, I came across a paper titled Cutting Wood Materials by Laser. This is fairly old, as this paper was written in 1975. On page 2, in a subsection titled How Does Laser Cut, we get a statement that reads, Marshall found that the ponderosa pine 0.005 kilowatt per hour cubic inch of material was used. Just as a quick conversion note, don't forget to change your inches into centimeters. Turning this 0.005 kilowatt hour per cubic inch into joules per cubic centimeter, we found out that our value was 1,098.429 joules per cubic centimeter for the vaporization of wood. That means that we can apply our volume that we just found, which is 9.24 times 10 to the 13th cubic centimeters, and multiply it by our J for CC value, which gives us a number of 1.01 times 10 to the 17th joules. But we are not done yet, as we do have to go on to the ground destruction. A little bit later into this video, I'm going to be going over how to calculate the vaporization values of things like granite, but for this, because it's a little bit ambiguous of what the actual material is, I'm kind of going back and forth on it. I'm just going to use the vaporization value of rock at a baseline level, which is 25,700 joules per cubic centimeter. Once again, using Nami, who has a listed height of 1.69 meters or 169 centimeters, and her representing 11 pixels, that means that our value is 15.36 centimeters per pixel. The diameter of the crater is 548 pixels, or 8,419 centimeters, and the height of the crater is 148 pixels, or 2,273 centimeters. For this one in specific, given its shape, we're solving for the spherical cap volume, which means that we get a volume of over 56 billion cubic centimeters. Taking our value of 56 billion cubic centimeters and multiplying it by 25,700 joules per cubic centimeter, we get a value of 1.4 times 10 to the 15th joules. And then once we add everything together, we get a solid number of 1.03 times 10 to the 17th joules in total for the tree and the ground, which is city level casual Enel. That's a lot better than what I had previously had for this calc, so I'm very happy that I came out with that, and I'm very happy that I found that paper on the vaporization of wood. On to the next calc. Luffy is fighting off against Enel when he was attacked with a wide-range lightning beam, moving a large distance to avoid it. Chapter number 279. For starters, we need to find the distance that they are away from each other before the actual lightning was shot. Because of the weird dimensions, we first need to find the size of Enel's wristband. In this chapter cover right here, we get a full view of Enel's body and his wristband. Enel has a listed height of 2.66 meters, and in this panel is 478 pixels, which means that we have a value of 0.005 meters per pixel. His wristband represents 17 pixels, or 0.09 meters. Because we don't get to see Luffy's full body, we need to get the diameter of his head. Luffy has a listed height of 1.72 meters in pre-Timeskip, and in this panel he represents 593 pixels. That gives us our value of 0.002 meters per pixel, whereas Luffy's head in this panel is 59 pixels, which means that it's 0.17 meters. Now that we have both of those, we first need to find out the distance between Enel and the panel. He is a lot closer, so that'll be easier to do first. The panel size is 701 pixels, where his wristband is 70 pixels. When plugging into our Aang size formula, we get that he's 0.67 meters from the panel. Using the exact same process for Luffy, where the panel is 701 pixels, but in this case his head is 8 pixels, we plug in and we get that he's 10.7 meters away from the panel. To get our total distance, we subtract those two together, 10.7 minus 0.67, and we get the total distance of 10.03 meters away from each other. Now we have the distance that we were away from each other, we need to get the distance that Luffy actually moved. Page after this, we get to see that Luffy is standing in front of Enel, and that is the distance that he moved right after it was shocked. We even see in the background the big hole that Enel left in the wall. We can start off by sizing Enel from the panel, where the panel is 797 pixels and Enel is 522. That means that he's 2.9 meters away from the panel. Using the same panel for Luffy, we plug into the Aang size calculator, but instead of using the Enel value with 522 pixels, we use the Luffy value for 100 pixels. Once we do that, we find out that Luffy is 9.7 meters away from the panel. To get our total distance, we just subtract those two together, the 9.7 minus 2.9, and we get 6.8 meters away from each other. Now subtracting both of the values from the first and the second, we take 10.03 and subtract it by 6.8, and we get 3.14 meters moved. So we have everything that we need except for the speed at which lightning was traveling. There's a lot of contention that goes around with lightning speed and how fast lightning would actually strike at. We do know that this is natural lightning because in SBS, Oda talks about Logia type users shaping things that are found in nature towards their advantage, which means that this is natural lightning. Values can range anywhere from 96,000 meters per second all the way up to 440,000 meters per second. In a study done by Amtech and Vision Research, they claim that lightning strikes at an average of 60 miles per second, which is kind of the low end of what we've seen so far and what I'll be using for this. Taking our time frame of total distance divided by that 96,560 meters per second, we get a time frame of 0.0001 seconds. Then taking the total distance that Luffy moved, which is the 3.14 meters, and dividing it by that time frame, we get a speed of 30,251 meters per second, which is Mach 88.1 or high hypersonic plus. What a very, very nice feat for Luffy. That's not all for Skypiea's speed though. On to the next calc. Nami is fighting with Enel as Luffy holds up the golden ball and she reacts and slashes away a lightning blast. Chapter number 283. This one should be fairly easy for us. For starters, we need to find the distance between Enel and Nami. Once again, Nami has a listed height of 1.69 meters, and in this case, the panel is 887 pixels, and she is 106 pixels, which means we could just plug into the Aang size formula, and we get to see that Nami is 10.098 meters away from the panel. Now, we could just call it there and say that Enel is close enough, but I like to be as thorough as possible. Because of such the weird angle that this is pointed at, we gotta Aang size Enel's face. Luckily, in this panel right here, we can actually get that size. Enel has a listed height of 2.66 meters, and he represents 198 pixels, which means that our value is 0.01 meters per pixel. As shown, his head is 15 pixels, which means that it's 0.2 meters. Using the same panel as before, with the 887 pixels as its panel height, and Enel's head being 86 pixels, we get that the distance between Enel and the panel is 1.5 meters. Subtracting Nami's distance by the distance that Enel is away from the panel, we get that the total distance between the two of them is 8.54 meters. Looking at the slash specifically, she made multiple movements of around 45 degrees and 90 degrees and maybe one more to keep it safe. We'll say that she moved her arm a total of 135 degrees with the baton being placed at the center of mass just before. Using this panel right here, we can find the size of Nami's arms. Once again, with a height of 1.69 meters and a pixel value of 208, we get 0.008 meters per pixel. With her arm being 67 pixels, that means that her arm is 0.5 meters in length. Now we move on to our C formula, which is just finding the circumference as well as the distance off of what she moved. C, or circumference, is equal to 2 times pi times the radius of the object. That means for our first value, we get 1.7. Now we need to divide the 135 degrees that we already established by a circle, which is 360 degrees. When taking 135 and dividing it by 360, we get 0.375. Now all that we have to do to get the total distance is multiply those two together, and we get to see that Nami moved 0.64 meters total. As we've already established, the lightning value is 96,560 meters per second. So to solve for time, we just take the 8.5 meters and divide it by the lightning speed, and we get 0.00008 seconds. Then we take the 0.64 meters that she moved and divide it by that time frame, and we get 7,248 meters per second, which is Mach 21 and falls into hypersonic plus. That's actually kind of amazing for some of the low tiers of Skypiea to be that fast already. On to our next calc. In response to a monster attacking the Straw Hats, Aokiji freezes the water between multiple peaks of Long Ring Long Land. Chapter number 319. For starters, we need to determine the distance between these peaks of Long Ring Long Land. In an earlier panel, it had shown that the Straw Hats are trying to get 3 peaks away from Long Ring Long Land, going from the left side. What's very interesting about the composition of Long Ring Long Land is how none of the peaks of it are actually shown within each other's horizon, meaning that they're over a horizon distance away from each other. In my One Piece Planet Size video, I determined that the distance to horizon in the One Piece planet is 169,866 meters. Luckily for us, we could use that same diagram that he gave us when talking about the peaks of Long Ring Long Land to determine the total distance. In the same map before, to determine our total distance, that means that the closest island represents one horizon distance, or 169,866 meters. Dividing it by its value of 14 pixels, that means we get 12,133 meters per pixel. The peak that they are attempting to get to is 126 pixels, which means that it's 2,742,138 meters away. For the total width of this, we can assume that it would at least be this panel right here, as all of the water in this general area is frozen. Using Nico Robin's listed height of 1.88 meters, we can figure out the dimensions of this total area. She is 21 pixels, or 1.88 meters, which means that we get a value of 0.08 meters per pixel. The width of the area is 3,200 pixels, which means that's 286 meters. So we could use that as our width for this, and now we need to get into our depth. When talking about the depth here, we have 2 possible interpretations that we can go with. Possibility A is that Aokiji froze the water so deep that it would extend the life expectancy of the ice, as the thermal interactions and solar interactions between the water and its surroundings would be halted for a longer time. Another possibility is that Aokiji's ice is much colder than regular ice, and it would have a higher heat threshold for change. While both of these are possibilities, I think I'll go with the first one because it's a lot easier to prove and is less guesswork if it's just going deeper down rather than it being colder, because I'd have to get a value which we don't really have. This study right here gives the average ocean depth of around 3.7 kilometers, and Fishman Island is 30 kilometers deep, so we can say that around 2.5 kilometers is the distance that he froze, or 2,500 meters. You might be thinking to yourself, but Earth is so much smaller than the One Piece planet, why would you use a Earth study that finds oceanic depth and not using something that is comparable to the One Piece planet? But as I said, Fishman Island is 30 kilometers deep, and the Skypiea Islands are 10,000 meters up. This is actually kind of consistent for cloud heights and other things like that, which means that they might not change that much. Once plugging these values into the formula for a rectangular prism, we get our volume of 1.9 times 10 to the 12th cubic meters. Now that we have our volume, we need to move on to getting our mass. To find our mass, we need to take our volume in cubic meters and multiply it by its density in kilograms per cubic meters. The average density for salt water is 1,050 kilograms per cubic meter. Multiplying our volume by that density, we get a mass of 2.06 times 10 to the 15th kilograms. We do know that Aokiji is freezing this, so we could assume that he's freezing it to 0 degrees. The sea at surface temperature is 20 degrees Celsius. Sea surface temperature does change with things like solar activity, clouds, and pollution, but you could use the average of 20 degrees Celsius. Because water freezes at 0 degrees Celsius, that means we have a temperature change of 20 degrees. The formula for energy found in temperature of change is mass in kilograms multiplied by the temperature change, or 20 degrees Celsius, multiplied by 4,184 joules. Which means we plug in our mass of 2.06 times 10 to the 15th, multiply that by 20, and then multiply that by 4,184. Once doing that, our final number is 1.7 times 10 to the 20th joules, which is island level, casual Aokiji, and Long Ring Long Land. This being the first DC showing from an admiral, I am absolutely astounded. Next calc. After taking a ship to Enis lobby, Luffy uses Gum Gum Rocket to move a vast distance, passing the Marines at the entrance. Chapter number 376. For starters, let's get some justification out of the way. The Marines who were walking out of the entrance were actually looking out at the water, as they did notice that something had flown by them as they were looking out towards the sea. It's not just one, it's not just two, but we can see multiple people looking straight out at the sea. We can confirm that they didn't even fully know that Luffy moved, as when they turned around and looked up, they saw him at the top, and we could see the question mark and the exclamation mark, indicating that they didn't even know what happened. With that out of the way, we can go straight into the calc. First, need to find the distance between Luffy and the guards. Once again, using the average height of a Japanese male of 1.718 meters, we can plug that value into the ink size calculator, where the total panel height is 949 pixels, and the height of the man is 7 pixels. In this perspective, we do not need to ang-size Luffy, as we know that he had just shot off of this specific point, so we can just ang-size from his original distance. Plugging into the ang-size formula, we get the distance of 166.32 meters traveled. As I talked about before, the standard time frame that we use for perception blitzes is 0.013 seconds, or 13 milliseconds. Taking 166.32 meters that he traveled, dividing it by that time frame, we get 12,793 meters per second, which is Mach 37, and that means that he is high hypersonic plus at the very beginning of Eni's lobby. Thinking back to our very first calc, he's Mach 5, and now he's Mach 37 doing the exact same thing. I would have really made this boy strong. Let's keep the ball rolling, moving into our next calc. While fighting Kalifa, Nami summons a cumulonimbus cloud and attempts to strike her with it. Chapter number 407. For starters, we need to find the distance between Kalifa and the cloud, as Nami wasn't the one shooting the attack here, it was the cloud above her. Kalifa has a stated height of 185 centimeters, or 1.85 meters. Taking Kalifa's height of 1.85 meters, dividing it by her pixel value of 197, we get 0.009 meters per pixel. The cloud being 288 pixels above her gives us our value of 2.7 meters between her and the cloud. In this panel right here is shown that she reacts to it using her devil fruit. Her devil fruit first appears by her ankles and then goes up her body, so we can use her full body as the distance moved here. It means that our distance moved is 1.85 meters. Our time frame is the distance between her and the cloud, or 2.7 meters, and dividing it by our lightning value of 96,560 meters per second. That gives us a time frame of 0.000028. Taking our distance move, or 1.85 meters, and dividing it by that time frame, we get a value of 66,050 meters per second, which is Mach 192, which means that a low tier of Eni's lobby, Kalifa, is massively hypersonic. What an amazing feat that so many people can get scaling off of. On to our next calculation. While going after Marshall D. Teach, aka Blackbeard, Ace clashes with him, causing the clouds in the immediate area to disperse. Chapter number 441. We first need to start off by sizing the clouds of the area. Weather.gov gives us a visual that says that clouds generally sit around 15,000 feet above the ground, which is 4.57 kilometers. In this panel, the 4.57 kilometers is represented by 55 pixels. That means we get a value of 0.08 kilometers per pixel. The base of the cloud is 158 pixels, which means that it's 13 kilometers, or 13,000 meters in diameter, whereas the height of the cloud is 117 pixels, which means that it's 9.7 kilometers, or 9,700 meters. Sizing this cloud layer by layer would probably be more accurate, but it is kind of misshapen, so I'm going to use the volume of a cone. Plugging that in, we get a volume of 4.3 times 10 to the 11th meters cubed. We can once again plug back in for our volume formula, which is volume in cubic meters multiplied by density in kilograms per cubic meter. This study right here says that clouds have a density of 1.003 kilograms per cubic meter. With all that being said, that means that the mass of the cloud is 440,554,711,000 kilograms. A lot of people really don't realize that clouds can get pretty heavy. We can use the same panel and the same values as before to find the total distance moved. Because afterwards none of the clouds are seen in the immediate area, we can just take the line going through the entirety of the page. The page diameter of 718 meters, that our total cloud movement is 59 kilometers, or 59,000 meters. Now we gotta move on to our time frames. Most clashes seem to happen fairly instantly, and these types of fights usually cause a massive movement in clouds, seemingly one blow to cause all of it. If these type of clashes would cause a very fast blowaway, we can use very short time frames of 1 second, 3 seconds, and 5 seconds. For our first time frame of 5 seconds, we take our distance move, or 59,000 meters, and divide it by 5, which gives us 11,937 meters per second. Doing that same process for the second one of the time frame in 3 seconds, 59,000 divided by 3, we get a value of 19,895 meters per second. And then the fastest speed that we will be using is itself divided by 1, which means that the fastest speed we have is 59,685 meters per second. Plugging into the kinetic energy formula at the very low end with the highest time frame, we get 3.1 times 10 to the 19th joules, which is large mountain level. It seems a little bit disingenuous to say that it took 5 whole seconds for them to disperse, but we're still going to say it just for the case of this video. Our second time frame of 3 seconds gives us a value of 8.7 times 10 to the 19th joules, which means that it's island level. And then at the very highest this feat can be justified for, we get a value of 7.8 times 10 to the 20th joules, our large island level. Ace and Blackbeard just really are demons. On to Thriller Bark. While fighting against the Straw Hats, Moria of the Thousand Shadows does an attack that splits the entirety of Thriller Bark. Chapter number 481. First, we need to find the size of Thriller Bark. Now this should be fairly simple, as we can see the entirety of Thriller Bark while Oars is standing on top of a ship in the middle. Oars has a listed height of 67 meters, which means we could use that as our value. Oars is 5 pixels, which means we get a value of 13.4 meters per pixel. The entirety of Thriller Bark at its diameter is 176, which means that the totality of Thriller Bark is 2,358.4 meters. We are treating Thriller Bark like it is a tropical island. The typical depth for a tropical island is around 500 meters, so we could use that, and we're treating this as a spherical cap. Converting everything into centimeters so that we could actually solve for the splitting of it. To get our radius of Thriller Bark, we're taking 2,358.4, dividing it by 2, to get our total radius of 117,920 centimeters. As I said before, the typical depth of a tropical island would be 500 meters, which means that it's 50,000 centimeters. Taking this into the volume for a spherical cap, we get a volume of 7.9 times 10 to the 14th cubic centimeters. Typical value to fragment something is 8 joules per cubic centimeter, as fragmenting it is breaking into smaller pieces. This was just cut, and it was cut down its center. There was not massive fragmentation done to the entire island, so we could take that half and say that it's 4 joules per cubic centimeter for the entire cut. There is some complexities that come down to sheer strength, but for the sake of this calculation, we could just stick to the half value of fragmentation, so we could use 4. Taking our volume and multiplying it by our joules per cubic centimeter value, we get a feat of 3.1 times 10 to the 15th joules, or large town level Moria. I'm not liking these values too much anymore. Let's try to amp it up a little bit. On Sabaody, the Admiral Kizaru is making the attempt to apprehend multiple high-value targets when Rayleigh challenges him and intercepting Yata no Kagami. Chapter number 512. For starters, let's find the size of Rayleigh's arm and his head for later. Rayleigh has a listed height of 1.88 meters. In this panel, he's 1,131 pixels. Taking his height and dividing it by his pixel value, we get 0.001 meters per pixel. His arm is 413 pixels, or 0.68 meters. That is 147 pixels, or 0.24 meters in total length. Now we can find the distance between Rayleigh and Kizaru. Kizaru has a listed height of 3.02 meters, and in this panel right here, he's 133 pixels, where the panel is 907. Plugging into our ink size formula, we find out that Kizaru is 14.706 meters away from the panel. Using the same method, but this time for Rayleigh, where he represents 73 pixels and the panel is 907, we find that he is 16.68 meters away from the panel. Subtracting those two together, that means they are 1.974 meters away from each other. Previously, we found Rayleigh's head size of 0.24 meters, and in this panel right here, it is 26 pixels, which means we get a value of 0.009 meters per pixel. We intercepted it midair, so we're drawing a line from Rayleigh's head up to where we see it in the air. That being 156 pixels means that Rayleigh jumped up at least 1.4 meters. Comes on to the reason why we had to find his arm. Rayleigh keeps his sword on his right hip. To unhilt his sword as well as swing, he must have done at least a 145-degree movement with his arm. Using the circumference or C formula as we call it, we can get the same value that we did before. 2 times pi times his arm, or 0.68 divided by 2, we get the value of 2.1. Taking 145, which is the degree of his turn, dividing that by 360, we get 0.4027 repeating. Taking our value of the first line, 2.156, and multiplying it by our second line, 0.427 repeating, we get a value of 0.68 meters. We take the distance that he jumped and add it to that, and we get a value of 2.28 meters. We are not done yet. Rayleigh and Kizaru are standing off perfectly in front of each other, and Rayleigh is going to jump up in the air to intercept something that's not aimed at him. That means that we have a standoff where Rayleigh jumps straight up in the air. That applies for a triangle. Given that they were set up in this manner, we can apply the Pythagorean theorem to get the full distance that he moved. And for the distance that they are away from each other, as well as how much he moved, we get to see that Rayleigh moved a total of 2.43 meters. Time frame, we're taking the distance that they are away from each other, or 1.974 meters, and dividing it by the speed of light, and we get a time frame of 6.58 times 10 to the negative 9th seconds. In the total distance that Rayleigh moved, or 2.43 meters, and dividing it by that time frame, we get a massive number in meters per second. Specifically, the number is 369,221,950 meters per second, which converts to 1.23 times the speed of light, meaning that Rayleigh at Sabaody is FTL. On to our next calc. After Whitebeard and the Marines exchange word, Kizaru attacks him with Yasakani no Magatama, and Marco intercepts this with relative ease. Chapter number 553. For starters, we can find the distance between Whitebeard and the platform. Marine is standing at the very front of the platform, so we could use him to angle-size the distance between it. The average Japanese male is 1.718 meters, so we can plug that into the angle-size formula, where the panel represents 1,203 pixels and he is 50 pixels. This means that he's 29.492 meters away from the panel. The same thing with Whitebeard, except for this time he has a listed height of 6.66 meters, where he represents 28 pixels and the panel is 1,202. Find that he is 204.16 meters away from the panel. Subtracting those two together, we get 174.668 meters. We're not done though, is we should probably take around half this total distance because we see that Kizaru actually jumped up and started moving. I don't know exactly where he ended up, but we do know that he moved forward, as before he was sitting in his seat and now he's up in the air very close to them. I think removing around half the distance should be good, which brings our total distance that he is away from him, 87.334 meters. Of the distance between Kizaru and Whitebeard, we can actually get the distance that Marco moved. Whitebeard is 49 pixels, which means that we get a value of 0.13 meters per pixel. Marco moved 329 pixels, which is 44 meters. Kizaru's text moving at the speed of light, we take the 87 meters that they are away from each other and divide it by the speed of light, and we get a time frame of 2.9 times 10 to the negative 7 seconds. Taking our distance that Marco moved to 44.7 meters and dividing it by our time frame, we get 153,510,066 meters per second, or 0.51 c, which is 51% the speed of light, or relativistic plus Marco at Marineford. An absolutely amazing showing from someone who's not a severe top tier at the time. You'd expect this type of feat out of someone like an Admiral or a Yonko, but we got this out of Marco. This video has gone in order when the feats occurred, which means that logically I should go into a very important set of Marineford feats. But what fun would that be if I gave you it right away? Let's move into post-Timeskip for now, and I'll touch on those feats a little bit later. After returning to Saba Odi to see his friends he's been missing for 2 years, Luffy reacts to a Kizaru beam from PX5 before defeating him. Chapter number 601. For starters, we can find the distance between Kuma or PX5 and Luffy. Pacifista robots are modeled after Kuma, and Kuma has a listed height of 6.89 meters. This panel, he is 67 pixels, which gives us our value of 0.1 meters per pixel. The distance between him and Luffy is 101 pixels, which means that they are 10.38 meters away from each other. Now, traditionally, I would absolutely hate using anime scenes to size a certain character's body parts because they're disproportionate from how they are in the manga, as Oda has his way of drawing, whereas the animators have their way of animating. But for the life of me, I could not find a full body picture of Luffy that I can actually use in the manga to get the size of his head, so for this case, we're just going to be using post-Timeskip Luffy in the anime. Now, post-time Luffy has a height of 1.74 meters, and in this he's 1,890 pixels, which gives us a value of 0.0009 meters. Specifically, Luffy's face is 214 pixels, which means that is 0.19 meters. This we can use the top of his forehead all the way down to his chin because that's what we found before, and we can see that Luffy's head is 139 pixels, which gives us a value of 0.0014 meters. The distance that he moved is 103 pixels, which means that he moved 0.14 meters. For a time frame, we're dividing the distance that they are away from each other at the beginning that I found by the speed of light. Gives us a time frame of 3.4 times 10 to the negative 8 seconds. Taking the distance that Luffy moved and dividing it by our time frame, we get a speed of 4,213,844 meters per second, or 1% the speed of light, which gives us sub-relativistic, very casual Luffy at the beginning of post-Timeskip. Absolutely love this type of showing because previous to this, the Pacifista were seen to be something that is so incredibly hard to defeat. Into our next calc. In the events of the Straw Hat's arrival on Punk Hazard, we learn that Akainu and Aokiji in their clash with Fleet Admiral froze and melted half of Punk Hazard, permanently changing its climate. Mention chapter 658. Starters, I would like to mention, as shown in this scan right here, that we are at an equilibrium of the two halves. An equilibrium is when all forces act upon the same object and are in total balance of each other. While Akainu and Aokiji did completely change its climate, we do know that this is at an equilibrium, which means that neither one is overbearing on the other. As if the magma were too hot, it would melt the ice. And if the ice was too overbearing, it would cause a forced change in material for the magma. Some of the things that would come into play to allow this to happen is temperature, atmospheric pressure, clouds, wind, and humidity. All of these must be affected for the climate to be permanently changed. Punk Hazard, we get reference back to a single map which shows the total landmass of Punk Hazard itself. On one half we can see the snow side, and on the other half we can see the magma side. Right in the middle is where it took place and where the first clash actually happened. While it most likely did not take place there the entire time, at the very center is where things are kind of normal. So we could use the hypothetical size of a mountain here and say that the mountain that is shown in the scan would represent the actual size of itself. This research study right here says that the average mountain at its base would be 120 kilometers, and here it's 9 pixels. That means that we get a value of 13.4 kilometers per pixel. The entirety of Punk Hazard is represented by 80 pixels, which means that it's 1,072 kilometers at diameter. And the total area of Punk Hazard, we're just multiplying pi times its radius squared. This means that all of Punk Hazard is 904,079 square kilometers, or 9.04 times 10 to the 11 squared meters. This graph given to us by NASA, we find out that vertical cloud structure can be around 8,000 meters thick, so we can use that as its average. Find the volume for what we already have, we take the area in meters cubed and multiply it by the height in meters. This means that the total volume of the area that was affected is 7.2 times 10 to the 15th meters cubed. Just taking into account to the weather, so we're going to be using the clouds, we take the same density as before of 1.003 kilograms per cubic meter, which gives us a mass of 7.25 times 10 to the 15th kilograms. Plug right back into the same formula that we used a while ago to talk about the altitude of a cloud. Set altitude plus the height of the center divided by 2 times 2. The average cloud sitting at 15,000 feet or 4,572 meters, we get the total movement of 12,572 meters. So again, we do know that a cloud would decline 6 degrees per 10,000 meters traveled, so we do 6 times the 12,572 divided by 10,000, and we get the number of 7.5432 degrees Celsius lowered. To find the stagnant cloud temperature, we're taking the room temperature and subtracting that first number that we got, and we get the total of 12.457 degrees Celsius. Now we're going into dew point. The dew point is a temperature to which air must be cooled to become saturated with water vapor. The dew point formula goes as followed. TD equals T minus 100 minus RH divided by 5, where TD is the dew point, T is the observed temperature, and RH is the relative humidity. Using the value of an 80% for relative humidity, as clouds would probably be around this point before they actually start raining and before they have too much water vapor inside, we get our value of 8.4 degrees Celsius when plugging in all that information. Now, finding our starting drop to move onto latent heat of condensation, we get the value of plugging in for mass as well as the values that we just found, and we get 2.9 times 10 to the 16th joules. But we still need to move on to the latent heat of condensation for a cloud, which is given through the formula that we used before. I'm not even going to get into this lengthy formula, but I'll show you guys it right here. And we plug in for a cloud temperature of 12.45 degrees Celsius. All of that comes out to 2,471,534 joules per kilogram. Plugging in our mass and multiplying it by that joules per kilogram that we just found, we get a value of 1.79 times 10 to the 22 joules. And then adding in that 2.9 times 10 to the 16th, our total energy release is 1.7929354 times 10 to the 22nd joules. Means that we have a hypothetical small country level Akainu and Aokiji. Wow, that was a lot to go through. Keep in mind that is hypothetical, as we don't really know the full parameters of how long it took for them to do that. That is kind of just assuming that it took like a very short time frame for them to actually turn the entire island like that. But it is still pretty cool to see that that's potentially what that feat could have been, as they fought for 10 days. All of that being said, we can keep that momentum going and get to our next calc. And first introduce the new admiral of the Marines, Fujitora, uses his gravity fruit to destroy a massive area in the tavern. Chapter number 701. This feat is not placed here to upgrade anything, but it is given to show the consistency of how much stronger that the people are at this time on the most casual sense possible. For starters, we can size the hole that Fujitora creates in the middle of the cavern. The crater is 571 pixels, which means that it's 89 meters in diameter, and its depth goes down 112 pixels, which means that it's 17 meters in depth. It is consistent because we do see the Straw Hats looking down into the hole, and it's very, very deep. Using cylindrical volume, we could apply its radius as well as its depth to find our volume of 2.15 times 10 to the 5th meters cubed. This study right here tells us that the density of solid granite is 2,691 kilograms per cubic meter, so we could use that to solve for mass. Once again, to solve for mass, all we need is our volume in cubic meters, and then we multiply it by our density in kilograms per cubic meter. Once doing that, we find out that our mass is 580,050,775 kilograms. This, I'm going to be using a little bit of a different interpretation that involves friction, which will kind of help me get my value that I'm going to be talking about. Friction is the force resisting the relative motion of a solid surface or fluid layers. Dry friction is a force that opposes the relative lateral motion between two solid surfaces in contact. It includes things like kinetic friction, which would cause thermal energy to be released or a high amount of thermal activity to happen, which involves heat. The interaction that's happening between increased forces of intense gravity as well as rocks such as granite, wood, and other materials leads to very hot and potential borderline fire-inducing points. All of that being said, with such intense gravity, we can almost argue that this is a vaporization point, which is what I'm going to be doing today. First, need a couple of values. Our first value that we're going to be needing is the specific heat of rock, which is 750 joules per kilogram, as well as the vaporization point of rock, which is 2,470 degrees Celsius, but it has a standard change of temperature at 2,450 degrees Celsius, which is what we'll be using for that. After finding those, we can move on to the latent heat of vaporization of rock, which has a value of 4.8 kilojoules per gram, or 4.8 million joules per kilogram, as shown by this study right here, which researches the estimated energy to vaporize a rock. We first start off by multiplying our mass by the specific heat of rocks, as well as the vaporization point of 2450, and that gives us this value right here, 1.08 times 10 to the 15th joules. After that, we solve for a second value of the latent heat of vaporization, which is 4.8 million joules per kilogram, and we get 2.8 times 10 to the 15th joules. Once adding those together, we get a total value of 3.9 times 10 to the 15th joules, which is a super hyper casual Fujitora large town level. You might think that that's underwhelming, so I'm not going to disappoint you with this next one. Let's get into it. Fujitora is fighting Law, attempting to take him out for abandoning his warlord status. He pulls down a meteor to which Doffy slashes into small pieces, reducing its impact. Chapter number 713. This one will kind of be a 2-in-1 package, as we can find destructive capacity and speed from the exact same calc. Previous video of mine, I calculated the size of the One Piece planet. It has a polar diameter of 480,000 kilometers. As atmospherically it seems fairly similar to Earth, we can actually take the value of the distance between the ground layer and the exosphere to get the value for what it would be on the One Piece planet using the exact same ratio. Since we determined that the One Piece planet is 37.825 times bigger than the Earth, we can use that as our value. NASA tells us that the distance of the exosphere is located between 910,000 kilometers, which gives us a base value of around 4,000 kilometers. Deriving a basic ratio, we take that 4,000 kilometers, turn it into 4 million meters, and then we multiply it by the 37.825. All of this meaning that the distance to the exosphere inside of the One Piece planet is 151,300,000 meters. This means that we can move on to our time frames. Now, when observing the actions that are done by Fuji, he was pulling down the meteors and it wasn't a perception blitz time frame, so we're not going to be using anything like that. People were able to look up and see it, but it was coming down very fast. Because it was coming down very fast and they were still able to see it, we can use 3 time frame values of 5 seconds, 10 seconds, and 15 seconds. The 15-second time frame, it is still moving at 10 million meters per second. The 10-second time frame, it is moving at 15 million meters per second, and at the 5 seconds time frame, it is moving at 30 million meters per second. Now that we have that, we can move on to sizing the actual meteor and getting its mass. Law has a listed height of 1.91 meters, and in this he is 4 pixels, which means that we get a value of 0.4 meters per pixel. In the case of this meteor, it's 109 pixels, which means that it's 52 meters in total diameter. It gives us a value of 73,824 cubic meters. On average, the density of meters is around 3,000 kilograms per cubic meter. Again, solving for our mass, which is volume in meters cubed multiplied by the density in kilograms per meter cubed, we get a total mass of 273,149,207 kilograms. Applying our 3 time frames per the same mass, we get 3 different massive results. At the very, very low end of 15 seconds, which means they were staring up at the sky for a whole 15 seconds as it was falling, 1.1 times 10 to the 22 joules, which is small country level. At its mid-ball, which means that they're staring up there for 10 seconds, we get 2.5 times 10 to the 22nd joules, which is, again, small country. But at its 5-second time frame, it's a 1.01 times 10 to the 23 joules, which is just country level. An absolutely insane feat. Oh, wait. Don't get stuff twisted. Don't forget, he still slashed it. Now, you, the dear watcher, might be thinking to yourself, but DC, look, Law cuts it in half right before that. And to that, I say you are absolutely right. But let's take a look at what Law is capable of. In the image above, we can see that Law's ability put at use when it cuts things isn't in the means of traditional swordplay. Law is able to cut things in half with absolutely zero resistance to it whatsoever. He does not play with oppositional forces when he slashes. Those slashes are entirely resistant-proof, baby. That means we continue off with that notion. We first need to find the size of Doffy's head. Doflamingo has a listed height of 3.05 meters, and in this scan right here is 24 pixels, which gives us a value of 0.012 meters per pixel. And in this case, his head is 24 pixels, which means that it's 0.28 meters in total length. In this right here, we can anxize the distance between the meteor itself, which is what we're in perspective of, and Doffy. His head is 19 pixels, and the panel size is 616 pixels, which means that he's 6.67 meters away from the panel once plugging it into the anxize calculator. In this specific panel right here, we see that the meteor moved even further after the slashes, meaning the distance that it traveled is our time frame. Once again, Doffy is 3.05 meters tall, and in this case, he's 74 pixels, which means we get a value of 0.04 meters per pixel. The distance to the meteor itself is 30 pixels, which means that it's 1.2 meters away. Taking the original distance that he was away from it of 6.6 meters and subtracting it from our new 1.23 meters, we get a total distance of 5.4 meters away. Before we continue on with our time frame, let's first figure out how much Doflamingo moved. The slashing style that we see Doffy take on is a one-arm stretch, extension, then drop. Then his other arm does the same thing. In the actual panel of the slashes, we can see 2 sets of lines, which means that there's 4 total movements. All of this means that he takes 2 100-degree swings, 1 for each arm, and then 2 90-degree drops, 1 for each arm. In this image right here, we can find the size of Doffy's arm. Where he's 3.05 meters and represents 351 pixels, we get a value of 0.008 meters per pixel. His arm is 200 pixels, which means that his arm length in total is 1.73 meters. Quickly to put that in perspective, Doflamingo is 10 feet tall exactly, and an entire human could fit in the length of his arm. We are once again moving back to our beautiful C formula, where in this case we're plugging in 1.7 as for Doffy. Plugging in Doflamingo's arm for the radius here, we get a value of 10. Then we move on to our actual movements. 120 degrees divided by 360 gives us 0.333 repeating, and then 90 divided by 360 gives us 0.25. We take those values and we multiply them by each other, and then multiply that by 2, and we get 7.27 meters and 2.7 meters. We need to add those two together because he is dropping his arm and bringing them up in total, so these need to get added together. We get our value of 10.0009 meters. We can now move on to our speed and getting our time frame. For this, we use the 5-second calculation speed. Taking the distance that we found Doflamingo was away of 5.4 meters and then dividing it by our speed, we get a time frame of 1.7 times 10 to the negative 7 seconds. Taking the 10 meters that we know he moved and dividing it by our time frame, we get a speed of 55 million meters per second, which is 18% the speed of light, which means that Doflamingo pretty casually is relativistic. So many characters getting so many beautiful feats. We love the Shishibukai being this strong. Ladies and gentlemen, boys and girls, we are finally on to the last feat and the best feat inside of One Piece, which comes from Marshall D. Teach, or Blackbeard. For starters, let's go over Teach and what he did. After Whitebeard's final battle of destroying Teach, he proceeds to absorb Whitebeard's newly lost fruit for himself. After doing this, he releases the uncontrolled power of the Gura Gura no Mi, chapter number 579. These quakes were so powerful that they had tsunamis that were reaching the shores of Sabaody. When we take a look at how high these waves are, we absolutely get dwarfed by them. We say that they're way further above the marine base, even at a further perspective. That very same marine base was hiding a man known as Juan Wolf, who has a stated height of 180 meters. Considering that some of the most damaging earthquake and tsunamis only reached a magnitude of 9.1 and had tsunami waves a height of 40 meters, I think it's very safe to say that we can use 9.5 for ones that are over 180 meters. We can start calculating this earthquake. Now, the method that I'm using is a little bit unorthodox, as I'm not using these standard calculations and formulas that most people would use. After reading a book, looking on a few threads, as well as watching a couple videos, I found out about this formula that we can use to calculate the magnitude of an earthquake. Of course, Richter magnitude is set on a base 10 logarithm scale. Now, this formula on the screen might look a little bit intimidating, but it's really not, because we're solving for two things. We're solving for A, which is amplitude in millimeters, and delta T, which is the time difference in seconds. Before anything, we need to talk a little bit about what seismology is. Seismology is the study of earthquakes and seismic waves that move through and around the Earth. Seismic waves are caused by the sudden movement of materials within the Earth, such as a slip along the fault line or during an earthquake. There are several different types of seismic waves, and they all move in different ways. The two main types are body waves and surface waves, or P waves and S waves. To understand where these come from, we need to talk about the epicenter versus the hypocenter. The epicenter of an earthquake is the location of the Earth directly above the surface where the earthquake occurred. This is used as a reference point to find out what is actually happening to these waves as they go from their original point. The epicenter is the surface above the earthquake, but the hypocenter is the focus point, or where it's happening itself. We get kind of lucky here because Teach is the epicenter and the hypocenter because he is releasing the earthquake from his own point. Now, you might be wondering to yourself, how do we even get these measurements? The values of the earthquake are recorded on something called a seismograph. These seismographs are getting a constant influx of information, but they're recording the highest in the amplitude that is received. Things that are traveling towards them are known as P waves and S waves. P waves, or primary waves, are the first waves to arrive at the seismograph. P waves are the fastest seismic waves that can move through a solid, liquid, or gas. S waves, or secondary waves, are the second waves to arrive during an earthquake. They are a lot slower and they can only go through solids. These scales may be linear, logarithmic, or have some complex relationship, but in this case, we would solve them in logarithms because we're solving on the Richter. To determine Richter magnitude at distance, we would use a nomogram. Let me explain to you its basic function. Let's say that the seismic sensor 5 kilometers away recorded a maximum height of S waves to be 100 millimeters. This nomogram, we would draw a line from the distance of 5 kilometers and put it up to our 100 millimeter mark. Would give us our value of around 3.5 on the Richter scale. However, as I said before, we can solve this through another way. It is solved in base 10s, a logarithm. A logarithmic base 10 function means that it's going to go up at a steady rate. If a 2.5 is equal to 50 millimeters, that means that a 3.5 is 500, 4.5 5,000, 5.5 50,000, 6.5 500,000, 7.5 5 million, 8.5 50 million, and a 9.5 on the Richter scale would be 500 million millimeters. This just means that we found the first part of our equation, the A. We solved for the amplitude in millimeters, which is 500 million. We haven't set up a seismograph, we don't have any seismic sensors, so how are we going to get the delta T, which is the time difference? Well, in this seismology lecture that I found, we get this quote. Last time we learned that we could obtain the rough estimate of distance in miles to an earthquake epicenter by multiplying the S and P waves time interval by 5.7. Basically, all I would need to do is find the distance and divide it by 5.7 and we get our time difference. That is very easy. So let's solve for delta T. If you remember back to when I was talking about Aokiji, I found the distance between long ring, long land. At that point in the calculation, I determined that we would get 2.7 million meters or 2,742 kilometers, which would translate into 1,700 miles in this case. Applying that extra distance that we found between the two lands, which we could say is very simple to say that the difference between Marineford and Sabaody would at least be one of Long Ring Long Land's peaks. Adding on that extra 105 miles that we got there, our total distance would come down to 1,809 miles, which we divide by 5.7 to solve for our delta T, which gives us 317.444. When plugging our A and our delta T into the formula, we get a Richter magnitude of 16.4. Richter magnitude of 6.4 would release 2.5 times 10 to the 29th joules, which means that Blackbeard is moon level. That is absolutely insane. He just obtained the Gurgura no Mi. He has absolutely zero idea of how to use it, and he releases moon levels of energy right off the bat? A feat that occurred on chapter 579 in pre-Timeskip was moon level. Can you imagine what had happened 2 years after he's had the fruit for a whole 2 years to learn it? He is probably an absolute beast with it right now. In terms of the scaling here though, this is where it's going to end up stopping. Outside of pre-Timeskip, the only arc that's really full of feats is Dressrosa, which I already covered. The feats in Tawano are just not good enough for me to give it to you guys because I don't want to waste your time on feats that are just going to disappoint you. I really hope that the days and days that I put into this video kind of gives you guys a reference point to where One Piece is scaling currently. As I'm sure you guys can see, the timestamps are linked so you can get to any calc you want at any point in time, so always feel free to come back and reference this video and show your friends or show whoever you're debating these calcs. At some point, these calcs will be uploaded to my wiki, which is the Lounge's Battle Wiki, but that won't be for a while so that people will still come back to this video, because it took me a little bit too long for me to just upload them on the wiki and have nobody ever come back here. I really want to thank each and every one of you for coming by and listening to me rant. I hope in the future I can stay your power scaling guy.